Hello students, welcome back to our channel Physics Gallery Asha Binu. This is your Asha teacher coming with the next lecture, the fifth lecture of our way optics. Today we are going to continue our Young's double slit experiment YDSE. In the last class we have discussed the Young's double slit experiment in detail. There we have discussed the position of nth bright band, y is equal to n lambda d by d, the position of nth dark band from the center O of the screen to n minus 1 by 2 lambda d by d. Okay, then the width of each bright and each dark is obtained as half lambda d by d. Everything we have discussed. And finally, the band width, fringe width beta also, which is the distance between two successive bright or dark bands, lambda d by d. All we have discussed, and today we are going to continue the same topic, Young's double slit experiment. We are going to continue the remaining topic, okay? And at first we are going to plot the intensity versus, we are going to plot a graph, intensity versus distance of fringes on the screen. Okay, we are going to plot a graph of intensity versus distance. That is, in y-axis we are going to take the intensity here, intensity I, and in x-axis this is the center O, first dark, first bright, second dark, second bright, third dark, third bright. Okay, then on the opposite side also, first dark, first bright, second dark, second bright, third dark, third bright, and so on. Clear? So we are going to take the distance, and we know each division is half lambda d by d. This is half lambda d by d. Each division is half lambda d by d. The width of each band is half lambda d by d. Here also half lambda d by d, and so on. Each width is half lambda d by d. Okay, clear? So what about the center position? Oh, what about the central position? Yes, the path difference is 0. We got a maxima here. So we can take a maximum position here. Maxima. From 0 to first minima, it is maxima. But at first minima, first darkness, no intensity. First bright, maximum intensity. Second dark, 0 intensity. Second bright, maximum intensity. Minimum intensity, maximum intensity, and so on. Okay, clear? Here also brightness, maximum intensity. Darkness, no intensity. Second bright, maximum intensity. Darkness, no intensity. Okay, so how to plot the graph? What will be the graph? Central maxima, maximum intensity. First minima, the intensity decreases to 0. The intensity decreases to 0. Again, from first dark to first bright, maximum intensity. Second dark, minimum intensity. Second bright, maximum intensity. Third dark, minimum intensity. Third bright, maximum intensity, and so on. Okay, clear? Here also, first dark minima, first bright maxima, maxima, minima, maxima, minima. Okay, clear? Maxima. Okay. Okay, so this is the intensity versus distance graph. This is central position, first minima half lambda d by d, first dark to first bright half lambda d by d, half lambda d by d, and so on. So this is the intensity versus distance graph. Clear? Okay. Okay, so in the last class we have discussed the position of nth bright, nth dark, band width, the width of each band, and so on. And this is the intensity versus distance graph. If so, Can you tell me what is the width of the central maxima? What is the width of the central maxima? Have you plotted this graph? Yes, good. So what is the width of the central maxima? Central maxima ranges from this point to first dark on either side of the screen. Okay, so how can you define this central maxima? It is the distance on the screen from the center O to the first minima, first darkness on either side. So this will be the width of the central maxima, half lambda d by d plus half lambda d by d. Clear? So I am going to rub this, hoping you have taken this much. Okay. So the intensity versus distance graph is now clear to us. Now we are going to take the width of central maxima. Width of central maxima. Okay, we understood it is half lambda d by d plus half lambda d by d. So how can we define this width of central maxima? It is the distance between the first minima on either side of the central maxima. Clear? So what is width of the central maxima? It is the distance between, for example, if the slits are taken very close to each other, the slits are always very close to each other. In order to observe, we have taken the slits S1 and S2 at a distance small d in the Young's double slit experiment in order to see the internal things. But the slits are very close to each other. This is the screen and this is the center point O. This distance is capital D. Okay, and this is the position of first dark. This is the position of first dark in opposite side. Okay, clear? Then this will be the central maxima. This will be the central maxima. Clear? If so, we know this distance is half lambda d by d. Okay, and this is also half lambda d by d. Clear? So what will be the total distance? That is y. This is y plus y. You will get the total width of the central maxima. So linear width is equal to 2 times y. Okay, that is 2 times half lambda d by d. Linear width is equal to lambda d by d, linear width of the central maxima. If so, what will be the angular width? What is angular width? This angle. Okay, this is angular width. If this is theta, this much is theta, the total angular width will be 2 theta. Angular width is equal to 2 theta. 2 times this angle. Angle is equal to arc length y by d. 2 times half lambda d by d divided by d. d 2. Angular width is equal to angular width of the central maxima becomes lambda by small d. Clear? So what is the angular width of central maxima? It is lambda by small d, and linear width is lambda capital D by small d. Clear? Okay, so in the last class, this is the continuation topic of the first part of Young's double slit experiment, where we have discussed the experiment in detail. Now the remaining topic, the first topic, the intensity versus distance graph. The second one is the width of the central maxima, linear width and angular width. Okay, clear? Is it clear now? Yes. So this is our Young's double slit experiment. This is our Young's double slit experiment. And now we are going to the conditions for sustained interference. sustained interference. The conditions for prominent interference pattern. The question will be like this. What are the conditions for the sustained interference? The first one is that the waves must be coherent. Waves must be coherent. What is coherent waves? Waves having same omega, angular frequency, we have discussed in detail in the previous lectures, and constant phase or phase difference. Constant phase or phase difference. Okay. Such waves are called as coherent waves. The second is that monochromatic. The source must be monochromatic. The source must be monochromatic. Okay. Only a single wavelength can be taken. Then only sustained interference, alternate bright and dark bands can be obtained. The third is the distance between the slits. Distance between the slits, small d, very small, and slits will be, that is very narrow, very small distance between the slits, and slits must be very narrow. Must be very narrow also. Clear? That is, the distance between the slits d must be very small, and the slits will be very narrow. Okay, very narrow and very close to each other. We will write like that. That is a good sentence. The slits must be very narrow, and very close to each other. Close to each other. The next is, the fourth one is, the screen must be at a comparatively larger distance from slits. That is capital D greater than small d. Okay. And finally, the amplitude A and intensity I of waves must almost equal, almost same. Then, if all these conditions are satisfied, that is, the waves are coherent, having the same omega or constant phase or phase difference, the source must be monochromatic, the slits must be very narrow and very close to each other, the source must be at a comparatively larger distance from the slits, and having the same amplitude or intensity, or almost the same amplitude and intensity, then the pattern, interference pattern, will be very prominent. We will get a prominent bright, dark bands on the screen. Clear? So these are certain conditions for the sustained interference. Okay. Clear? So this is the topic continuation of the Young's double slit experiment part 1. After studying that, only come to this portion. Okay, so these are the conditions for the sustained interference. And finally, the last topic, special cases of interference. That is, what happens to the Young's double slit experiment if we use white light instead of the monochromatic light? Instead of monochromatic light, if we use instead of monochromatic light, if we use white light, what happens? We will obtain the central maxima as such, but followed by different colored patterns. Okay, we get central maxima surrounded with what is this? Surrounded with different colored patterns. Okay, so what happens instead of monochromatic light if we use the white light? If we use the white light, which is the combination of 7 colors, we get the central maxima as such, because all of the light falls at the central point without any path difference. Central maxima is obtained as such, which is followed by the different colored patterns. Then next one, what happens if we conduct YDSE in a medium? If the Young's double slit experiment is conducted in a medium, if we conduct it in a medium, what happens? In medium, the wavelength in medium becomes wavelength in air by refractive index of the medium mu. Do you understood? From Snell's law, sin I by sin R is equal to ray-optics, mu2 by mu1, which is equal to v1 by v2, which is equal to lambda 1 by lambda 2. If the first medium is air, okay, we can write mu by mu in air, mu in medium by mu in air is equal to lambda 1, that is in air, by lambda in medium. So lambda in medium becomes, what happens? Lambda in air, mu in air is 1, it is equal to 1, mu 1, it is equal to 1, in air it is 1, then lambda m is equal to lambda a. Oh, what is this? Lambda m is equal to lambda a, okay, by lambda in, that is mu in medium. Clear? Okay, so what happens to the wavelength? What happens to the wavelength? The wavelength decreases by mu. Therefore, the bandwidth beta also, fringe width beta also becomes lambda medium capital D by small d, or lambda A by mu capital D by small d. Beta in medium becomes beta in air by mu. Okay. Clear? So instead of monochromatic light, if we use white light, we will get a central maxima followed with the surrounded with the colored, different colored patterns, fringes. Then if the YDSE is conducted in a medium, the beta, bandwidth, everything, the position of nth bright band, there is also lambda present. Okay, so position of nth bright band, position of nth dark band, width of each bright and dark band, bandwidth, everything decreases by the factor mu. Okay. Similarly, if we use violet light instead of red, if a question is like that, what happens to the bandwidth if we replace one of the color with another monochromatic color? So what happens? Yes, the third case I am writing here, the third case, if violet is replaced by red. If violet is replaced by red, what happens? Beta is equal to lambda d by d. Lambda of red is greater than lambda of violet. So beta of red will be also greater than beta of violet. That is the thing. Okay, so when one color changes, the wavelength changes. If the wavelength increases, fringe width increases. If the wavelength decreases, fringe width decreases. So all of these were the extra points which we have to discuss about the Young's double slit experiment. All the important points we have already discussed in the previous lecture. Okay, take this much of notes. Clear? So this was all about our interference, our Young's double slit experiment, very important topic of wave optics. Always frequently asked questions from wave optics is regarding our interference. Okay. So we are going to one or two numericals also. Question number 1. For example, if lambda is equal to 5000 angstrom. Okay. 5000 angstrom. Wavelength of the monochromatic light, small d, the distance between the two slits is equal to 1 millimeter. Capital D is equal to, we can take it as 1 meter. Okay. The question is, find the separation between third maxima and 7th minimum. If the question is like this, what is your answer? In a Young's double, everything will be given. In YDSE, the wavelength used has the monochromatic light used has a wavelength of 5000 angstrom. The distance between the two slits is 1 millimeter. The distance of the screen from the slit is 1 meter. If so, find the distance separation between third maxima. That is the position of third bright band. N lambda d by d. You will write 3 lambda d by d. Okay. The position of 7th dark, 2n minus 1 by 2 lambda d by d. Do you understood? 2 into 7, 14. 14 minus 1, 13 by 2 lambda d by d. If so, what is the separation? Y of 7th dark minus y of 3rd bright. Okay, 13 by 2 is 2, 6 are 12, 6.5 lambda d by d minus 3 lambda d by d. What will be the answer? 3.5 lambda d by d. Everything is given. So we will write the separation as 3.5 into 5000 angstrom into angstrom means 10 raised to minus 10 into, then capital T is 1 meter by 1 millimeter, 10 raised to minus 3. 5 into 525, 2, 5 3s are 15, 16, 17. Then how many zeros? 1, 2, 3, 10 raised to 3, 10 raised to minus 10, and 10 raised to plus 3. 3, 3, 6, 4, 17.5 into 10 raised to minus 4 meter will be the answer. You may check. Okay, you may check it. You have to analyze whether the answer is correct or not. Almost the same thing. Okay, so whatever may be, the procedure is the same thing. What is the procedure? You have to take the position of nth bright band, third bright band, nth dark band, 7th dark band. So what is the distance between the two? It is equal to y 7th dark minus y third bright. Clear? Okay. The questions will be like this. Okay. Then another question related. Have you written? Yeah, ma'am. Already you have read everything. Have you written? Have you written? Okay. The question will be like this. The second question related. Our central bright, third bright, and fifth bright. The question is like this. If the distance between the third bright and the fifth bright on either side of the central maxima, if the distance between, if the distance between third bright and fifth bright, third bright and fifth bright on opposite side of central maxima is 1.5, what is that? 1.5 meter. Find the bandwidth. Find the bandwidth. How to write? This is 3 lambda d by d. Okay. This is opposite side, 5 lambda d by d. So this much distance is, the total distance is y3 bright plus y of fifth bright on opposite side, the total distance. That is, we can write it is equal to 1.5 meter is equal to 5 plus 3, 8 lambda d by d. Okay, so what is lambda d by d? Lambda d by d is equal to 1.5 by 8. That is the bandwidth. So what is bandwidth? 1.5 by 8 meter will be the bandwidth. Clear? So these are the special type of questions related to this interference. Everything we have discussed in detail. Okay. So hoping you understood the topic. Clearly, this is a small segment related to the first part of YDSE. This is the continuing segment. After studying that, follow these also, then interference becomes perfect. That is, already we have discussed what is interference in detail. In one of the lecture, third lecture, we have discussed interference in detail. Thereafter, Young's double slit experiment, and this is the continuation of that portion. This much is pending in that lecture. Okay, so hoping you understood the interference very well, and till the next lecture, study well. We will come soon with the next topic called as the diffraction related to the wave optics, another important topic. Okay, so winding up the class today. And before that, once more, this is our channel, Physics Gallery Ashabinu. See you in the next class.